Imagine blasting off from Earth and arriving at Jupiter in just 60 minutes. It sounds like science fiction, but what if we could actually achieve it? Jupiter is on average about 778 million kilometers away, which varies from 588 to 968 million kilometers over our orbits. So with current technology, the journey takes years, not hours. For example, NASA's Galileo spacecraft, launched in 1989, took just over 6 years to reach Jupiter, and Voyager 1, launched in 1977, took 2 years. Even our fastest probe to date, New Horizons, needed about 13 months to fly past Jupiter in 2007, and Juno, launched 2011, took 5 years to arrive in 2016. Every mission so far has measured travel time in years or months, not minutes. To cover such huge distances in just 1 hour would require speeds on the order of 200,000 kilometers per second, roughly 70% the speed of light. No current rocket comes anywhere near that. Even NASA's Parker Solar Probe, the fastest human-made object, only reaches about 95 kilometers per second, 340,000 kilometers per hour, near the Sun, merely 0.03% of light speed. Light itself takes about 40–50 minutes to travel from Jupiter to Earth, so squeezing it into 60 minutes implies near light speed travel. Even 0.7 c is unimaginable in practical terms. At 1 g, constant acceleration, it would take many months to reach that speed, and the resulting g-forces would be instantly fatal. In short, the physics and the rocket equation fuel requirements just won't cooperate with a 1-hour Jupiter Express. Scientists love thinking up wild ideas to beat these limits. Warp drives. In theory, a warp drive could cheat the distance by bending space itself. Sci-fi fans know the concept. A spacecraft sits in a tiny bubble of normal space, while space in front of it contracts and space behind expands. In 1994, Miguel Alcubierre showed this could work on paper without locally breaking Einstein's speed limit. NASA even built a tiny warp field interferometer to test for such effects, though no positive results have emerged. The catch was that Alcubierre's original idea needed exotic negative energy, or dark energy, to power the bubble, something we don't have. However, recent theory by Fuchs et al. Suggests a warp bubble might be made with normal matter. Unfortunately, even this model only allows speeds extremely close to, but not exceeding, light speed. In other words, warp drives remain tantalizing theory, not a ready solution for jumping to Jupiter. Wormholes. General relativity also allows for space-time wormholes, tunnels connecting distant points in space. In principle, a stable tunnel to Jupiter's orbit would let you pop there instantly. But wormholes are purely hypothetical and would likely need exotic negative mass matter to stay open. Experts warn that a human traversable wormhole is probably forbidden by physics. No wormhole has been found, so this shortcut is only theoretical. Nuclear rockets. Back in reality, we are working on much less flashy but more feasible tech. Nuclear thermal rockets use a reactor to heat propellant to far higher temperatures than chemical fuel can reach, roughly doubling exhaust velocity and halving trip times. NASA and DARPA's DRACO program is even building a prototype. A nuclear thermal rocket test is planned for 2027. If successful, nuclear rockets could cut travel to Mars months roughly in half and shorten outer planet trips. They won't get us to Jupiter in an hour, but they might shave travel times from years to months. Antimatter. As an exotic energy source, antimatter has enormous appeal. Antimatter annihilation releases about 10 billion times the energy of chemical fuel. In theory, A true antimatter engine could accelerate a ship to unprecedented speeds. But producing and storing even tiny amounts of antimatter is beyond our capabilities today. It remains a speculative idea far from practical use. Laser light sails. Looking to the stars, projects like Breakthrough Starshot propose pushing tiny probes with ground-based lasers. Starshot aims for microsails, hitting 20% light speed, to reach Alpha Centauri in decades. While that's geared to small probes, it shows laser-driven ships could achieve huge speeds. Scaling that up to carry astronauts to Jupiter is a massive engineering leap, but it's another idea on the table for ultra-fast travel. One more quirk of physics is special relativity. If you could magically reach near light speed, time for you would slow down relative to Earth. For example, astronauts on board might experience far less time passing while years pass outside. Cosmic ray muons created in Earth's atmosphere are a real-world example. They reach the ground because time dilation extends their brief lifetimes. In principle, a 60-minute Earth frame trip could feel shorter to the travelers. However, this doesn't help the actual trip time or energy. From Earth's view, it still took an hour, and you still need to accelerate to 0.7 c. First, time dilation is fascinating, but it doesn't give a shortcut to Jupiter in human terms. Another problem is acceleration. The famous rocket equation means every extra bit of speed requires exponentially more fuel. Even if you could carry exotic fuel, you'd need almost all your ship's mass just for propellant, with hardly anything left for crew or payload. And remember the G-forces. Accelerating quickly enough to get to 70% light speed in minutes would subject you to millions of G. Nobody would survive. Real rockets also have to decelerate. You can't simply stop a spaceship in seconds. So, in addition to physics limits, these practical issues make a 60-minute trip infeasible. Today, NASA focuses on more modest improvements. Voyager 1 1977 famously used gravity assists and reached Jupiter in about 2 years. New Horizons 2006 flew by Jupiter in about 13 months on its way to Pluto, though Pluto itself took nearly 10 years to reach. The upcoming Europa Clipper mission to Jupiter's moon Europa is planned for roughly a 3-year flight using the new Space Launch System, and Europe's JUICE mission to Jupiter's moons will take about 7.6 years. Even Apollo's crew took 3 days to reach the moon, only 0.0026 AU away, which puts into perspective how far Jupiter is. For a bigger picture, Voyager 1 still traveling only entered interstellar space in 2012, and it would take 75,000 years to reach the nearest star. These feats are impressive, but they remind us, reaching Jupiter remains a multi-year endeavor with current technology. Even if some ultra-advanced propulsion could send us to Jupiter so fast, the engineering challenges are astronomical. For example, NASA's Juno orbiter, which took 5 years to arrive, carries a titanium vault around its electronics just to survive Jupiter's intense radiation. At 0.7 c, even micron-sized dust particles would strike like bullets, so the spacecraft would need massive shielding. Then there's the issue of slowing down. How do you stop or enter orbit in just minutes? Communications with Earth would be delayed and severely Doppler shifted. And any crew would face lethal radiation and weightlessness. In short, the practical roadblocks, from shielding to navigation to life support, are just as daunting as the pure physics of speed. So, can we reach Jupiter in an hour? Not with any technology we have today, and probably not anytime soon. But asking this question is a fun way to stretch our minds. Every speculative idea, from warp drives to wormholes to advanced rockets, pushes the boundaries of physics and engineering. Future breakthroughs may surprise us. The journey of discovery has only just begun. After all, history shows that things once deemed impossible eventually happen. Asking bold questions like this connects learning with imagination and drives innovation. If you enjoyed this space adventure, please subscribe and like, and leave a comment below. I promise to reply to everyone. So keep exploring, and I'll see you in the next video. Thanks again, and may your curiosity be as boundless as space itself, truly limitless. Remember, curiosity is the rocket fuel of science. Until then, stay curious, keep looking up, and enjoy the journey.